So the next unit, or the unit right now, is forces, and it covers 2 chapters of your textbook. Has anyone looked at the textbook so far? Raise a show of hands how many people actually looked at the textbook. Yeah, you barely will need it, because as you can tell from the videos and the PowerPoints and the way we actually teach each other and discuss, you will barely need the textbook. Extra readings, you can go for it, but honestly, I don't think it's going to add anything to your physics understanding. Okay, at least in the compressed time frame that we have to finish this course. Okay, so concept and definition. All right. Okay. So how many people have heard the word force before? Okay. So whenever you actually hear the word force, mostly in a physics context, okay, or in a physics setting, you should either be thinking of either a push or a pull. How do you know that a force existed? Go ahead, copy. So how do you know that a force actually existed? You're gonna be seeing something, or someone either got pushed or a pull. But yes. Oh, first. Yes. Okay. No problem. Oh yeah. Sorry. Maybe the different title. Okay. However, do you actually have to see an actual push or an actual pull to actually know that there's a force that's being, present? Or could you still, put a force in and nothing would move? Does every force make something move? Did I move the wall? Did I exert a force? You can bet my hip is gone. All right. So yes, usually there's a push or a pull. What if there isn't? That's what Newton's laws are for, and we're going to cover them in a couple of days. But in general, a push or a pull. Which means if there's either a push or a pull, that means there must be a what? There has to be a direction. So right there, what do you know a force fundamentally must be? It must be a vector. Yes, a force must be a vector quantity. But now, after like 2 insane weeks of doing kinematics, you know that we usually start with vectors, and we can still think of them as what at the end of the day? Scalars, either positive or negative. Okay, again, you are more than welcome to use whichever way of thinking. However, I'm going to be mixing the two just to get you to see both ways. Okay, so a force is a vector quantity. All right, let me actually have this to know what you guys have. So a force must have a direction. A force must have force must have a direction. There we go. Okay, so sorry, the last one should have said must have a direction. Oops, sorry. So it should say must have a direction. Okay, all right. The symbol is coming up. It's coming up. Sorry. Oh, okay. Oh, sorry. Those are compressed slides. Sorry for that. How many people would like to take a guess at the symbol for force? I mean, what's the most obvious choice? Layla? Why is it not F small? I mean, you are right, but also the question is, always play devil's advocate. Why not? I mean, if you're saying it must be that, that must be a hint that the F small is used for what? For something else. Anybody would like to take a guess? Sure, as a subscript, right? I, and for initial and final. But what as an actual symbol itself? Not as a subscript, like as a big font thing, but with a small f. Anyone? What do you call this? Or this? Rhythm, keep going. Pitch, frequency. Lowercase f, almost exclusively in physics, is what? Frequency, okay? Which will be in the waves and sound unit, and we will cover so much about it, okay? Now, what do you think? So what was the symbol for force? F. But it must have a what on top of it? Technically, it must be a vector sign. There you go. Capital F. Please always make sure it's capital F, as I just said. Capital F with an arrow on top. It must have a direction. Okay? All right. Types of forces. Types of forces. Okay. There are two, everyone. There are 2 types of forces. 2 types of forces. The good news is, in grade 11 and 12 physics, we are only responsible for one of them. The other kind, You do not touch it, and I'll tell you why. So there are two types or categories or groupings or classifications, any way you want to say it, of forces. The first one is called fundamental forces. Fundamental, or the most essential forces. Okay, fundamental means what? The concrete, like the basic building blocks of forces. Fundamental forces. What are the fundamental forces? They are a group or a set of how many? 4. If anyone here ever watched, advanced physics, like PBS or National Geographic, if you heard about Neil deGrasse Tyson, how many people know Neil deGrasse Tyson? Or Brian Greene, or Brian Cox, the one where in the video I showed you two weeks ago. All of those people, do you think what do you think they studied actually? Physics, purely nothing but what? But physics in different kinds. Neil deGrasse Tyson is an astrophysicist or a cosmologist, like Stephen Hawking. Brian Cox is an experimental physicist. Brian Greene is a theoretical physicist, which was my degree, okay? We're lazy people. We just like to do things on the board. We never like to go into a lab, okay? Like we're anti-engineers, okay? 4 forces that are the reason why everything happens the way it does. You will only study them if you choose to go into a physics major. Doesn't mean I love you more. It just means that you will only really see them and dwell into them only if you go into advanced physics. Do other people study those forces? Very, very, very rare. Groups of people other than physicists study advanced physics. Like who? Chemists. If you're a chemist, you're technically doing what? You're doing what? Physics. What's the most important particle in chemistry? The one that keeps jumping between atoms and making reactions happen. Electrons. Electrons is a part of what? It doesn't get more advanced than electrons. Advanced physics. Who else studies it? Well, some engineers. Here's the thing. Civil engineers? No. What do civil engineers study? What do they study? What's that? Concrete. You don't need to know advanced physics for concrete. You just need to know physics. How about mechanical engineers? Do you think they study advanced nuclear physics? No way. How about chemical engineers? What do you think? How many people think that chemical engineers need to study some advanced physics? Yeah. I mean, chemical engineers must study what? Chemistry. At some point, they still need to know basic electron structure and movement. How about electrical engineer? It's in the name, electrical, electron, charges moving through current. That's what we're going to do in circuits, okay? Barely that's it. Okay. The good news is we're not going to touch it. We're going to, by the way, just so you know, the only thing you're responsible for in this course about fundamental forces is what you see in these slides. Nothing in the textbook, nothing anywhere else. What's the other category of forces? Okay, it really doesn't have a set name. This is what I like to call it. I like to call it what? Engineering forces. Because to me, it is a perfect description of what it deals with and who actually uses it. Okay? So how many fundamental forces did we say there are? 4. No, that's it. By the way, they've already agreed. There's only 4. Nothing else probably will be discovered. Engineering forces? Really, there isn't a number. Why? It depends how complex your problem gets. So in grade 11, we'll study some engineering forces. In grade 12, we'll add 2 or 3 more. In first year physics, whether you do science or engineering, you'll add probably one more, and that's it. So if I would guess, I'd say maybe no more than 9, 10 tops. They are a multitude. What does multitude mean? What's another word for multitude? Many, okay? A number of. That are dealt with on daily basis. So I don't really care about advanced physics when I walk. But I do care about what? Engineering forces. Daily basis that are relevant to how things are built and how they operate. I mean, you could argue that, well, also how they operate depends on what? Advanced, like my cell phone or this depends on advanced physics. Sure, but you know what? Kind of like what chemistry does. Like Miss Young, for example, sometimes she doesn't talk always about the electron, but she talks about the big reaction, like the tube. So you bulk it up, okay? I like to say that they are the forces that engineers care about when designing, building, and testing things. Okay, so that's why I like to call them engineering forces. Could they have another name? Maybe. I think the first time I taught physics 10 years ago, I think I used to call them daily forces or bulk forces. But engineering forces sounds scientific, and it's really, really true. If anyone here is ever going to major in engineering, those are the forces you need to care about. That's another reason why I like to call them that. Okay, so let's start with the 4 fundamental forces. Okay, fundamental forces. How long have they been around? Or, well, they've been around since the beginning of the universe. But how long have they been starting to be understood and discovered? 1930s, since these big names of Einstein, Heisenberg, Schrodinger, all of these names start to actually think what is really at the very, very core of any matter. Okay, so since 1930s, physicists have agreed that there are 4 forces, well defined now. I cannot even dare to say well understood. If we truly understood them, there would be nothing else to actually discover. Okay. By the way, all the Nobel Prizes in physics, almost 99% of them that you hear about every single, oh my God, today is the physics one. Or was it yesterday? Well, actually, look it up. Because the peace one was done and the literature one was done last week. So I think they start the science ones with the physics. So responsible for every single event that happens in the universe. So you hear about those big names winning Nobel Prizes. They're not winning for engineering forces. They're winning for fundamental forces. Discovering things about neutrons and protons and electrons and the structure of the atom and string theory and all these stuff. Fundamental forces. What are they? In no particular order of importance. All of them are equally important. Number 1. Can someone read that first word of number 1? Gravitational, not what? Not gravity. One thing in grade 11 physics is we start actually knowing how different, yet how similar, but also how different they are. Okay, gravitational force. Number 2. The electromagnetic force. The electromagnetic force. Okay, 2 done, 2 to go. 3. Strong nuclear. Don't you dare say nuclear. Okay, you're not Homer Simpson. Nuclear force. Actually, George Bush once called it nuclear. Okay, strong nuclear. Okay, here's a guess. If there's a strong nuclear, what do you think there is as well? If there's a strong nuclear, there's got to be a what? The opposite, which is? Yeah, you're right. Weak nuclear. Absolutely. They ran out of names 70 years ago. But fittingly enough, it's actually quite appropriate for what it does, or what it is, I should say, and what it does too. Okay, so gravitational force, electromagnetic force, strong nuclear force, weak nuclear force. Okay? We will just talk about the basic properties of each one. Start with the first one. Yes? Sure. Yeah. Okay, so flip the page, I think, or let's go with the first one. Gravitational force. What does the gravitational force do? Can anyone guess? Does it push things apart or does it bring them together? Right now, what's my relation to the Earth? Am I flying away or stuck to it? So what does it do? Is it a repulsive or an attractive force? Gravitational is never repulsive. It always brings objects together. Okay? Here's how simple gravitational force is. The only thing it cares about is the what? Is the mass of the object. It literally does not give a damn about any other property. It doesn't care about the color of the objects. It doesn't care about the size. It doesn't care about the atomic structure. It doesn't care about, it just cares about one simple number. How heavy or how light. Okay? So it does not care how light or how heavy. It just needs to what? To actually have a mass. Here's a question for you. Can anyone take a guess? Or maybe some people know. No? Yes. What's the only particle in the entire universe that has no mass? Zero mass. Literally 0 kilograms, not an approximate. 0 kilograms or grams or whatever is its mass. It's nothing in mass, but it still exists. And if it didn't exist, you wouldn't exist. Say again? But atoms have mass. Think about it. How many people did chemistry here? Or grade 11? How many people have heard of the atomic mass? You still need a what? The carbon mass and the oxygen mass to calculate the atomic weight. So not there. And by the way, just okay, you know what? I'm glad you said atoms. Can someone repeat what question I asked? I asked what? I did particle. Particles are not atoms. Do you see me? Atoms are made of what? Of particles together. Anyone? Shadi. Photon. How many people have heard of the photon? What does the photon do? Like, what's the basic idea that you can understand what a photon is? Photon is the particle that carries what? Carries what? Light. Light has no mass, but it has what? It's a pure bundle of energy. Have you ever heard of quantum mechanics? It was discovered by Heisenberg. No, sorry, not discovered. Founded by Heisenberg and Einstein to study light, and from light came everything. Okay, so the only particle that does not care about the what? The gravitational force is the what? Because it has how much mass? Zero. How can something that has no mass care about the force that pulls everything based on its mass? Okay. There is a gravitational. Do we expect a gravitational force to be between two galaxies? Yeah, because what's so special about galaxies? They have huge what? Do you still expect a gravitational force to be between two electrons? Theoretically. Do you expect it to be huge or unbelievably close to zero? But does it still exist? That's the whole point. It doesn't matter how light the thing is. If it has a mass, it's still gravitationally attracted to something else that also has what? That also has mass. Mass is the only currency the gravitational force deals in. Here's one interesting thing about the gravitational force. By the way, just so you know, one thing you need to know in this course is, listen up, the strength range of these forces. Do you think this is the weakest or the strongest force? How many people say it's the strongest? How many people say it's the weakest? How many people are just not sure? So half of you should be not sure, unless you took physics 11 before or you watched so many documentaries with Carl Sagan. It's actually the weakest. I'll give you actually everyone. I'll actually give you two ways to think how weak it is. Number one, eyes on me. One of my profs, physics prof, I feel sometimes that I channel this guy. May he rest in peace. When he passed away. But this guy was a freaking genius. He looked like a construction worker. No, seriously, Dr. Victor Elias at Western, theoretical physicist, PhD from MIT, worked with so many Nobel Prize winners, shows up, bald, big beard, burly guy, boots, ripped jeans, construction worker. He was both a physicist and a poet. He actually used to compose symphonies for London Orchestra, downtown. He did not look the part. But when he talks, swear to God, you need a dictionary because that's how elevated his English is. He once said, he held a piece of chalk, and he was like, I think he was 70, about 15 years ago. He was like, I'm a 70-year-old guy, and he was actually going through chemotherapy, and he was like, I'm preventing the Earth from pulling this chalk down. He's preventing the entire freaking planet from what? From that. So do you think gravity or gravitation is a strong or a weak one? If it was strong, what should happen to my hand? Is that happening? That might happen in 5 minutes. Okay, those are good exercise, by the way. But is it happening? So what can you say about gravitational force? It's so freaking weak. Here's the other proof that it's weak. Only 5 years ago, in 2016, they discovered what's known as the gravitational wave. They won the Nobel Prize for it. But it took 100 years after Einstein predicted them to be discovered. Why? Because they are so what? They are so weak. When something, okay, think about it this way. Question. Do you think we have now in 2021, do you think we have good enough scales to put this on and measure its mass? Yeah, oh yeah. We have things that could measure atomic mass. What if something is so small? You need what kind of device to detect it? What if something is so small or so weak? Yeah? Say it? But what's so special about the device? It needs to be very what? Very sensitive, very accurate. Guess what? It took until the year 2016 to actually come up with what? With wave detectors to detect what kind of waves? What kind of waves? So freaking. Okay, you want to know how weak it is? What did it take? It took the collision of two black holes. Yes, yeah, that's holy crap, yes, or more. Two black holes. By the way, how heavy is a black hole? Insanely heavy that it could suck what into it? Even light cannot escape. That's why it's called a what? Black hole. By the way, so you might think, if it sucks in light, How do they see it? By the pure absence of light around it, or the bending of light. Okay, that was basically one of the proofs for Einstein's theory of relativity. But my point is, it took two freaking insanely dense, those are cute but dense, colliding, disturbing the space-time around them, and sending what? Gravitational waves through light years until they got to us. But then we had detectors to actually what? Beep. They gave a spike. And that's how we knew that gravitational waves what? Existed. Almost every day we get more proof that Einstein was right every damn step of the way. Things he predicted with pure math, like Sheldon, and they're being proven by experiments and labs every single day. Is it making sense? That's how weak it is. So it is the weakest. Always remember my supervisor. He stopped a piece of chalk from falling, and he was 7 years old, going through treatment. All right, so it's the weakest of all forces. Again, it does not care about any properties of the objects, but their masses. By the way, just so you know, I realize that those two statements might be contradicting, right? I'm saying here it doesn't care about anything but what? But I'm also saying it doesn't care about what? How I'm saying it doesn't care how light. You still have what? You still have gravitational force, even if you have a super light mass. Okay, so that's what? Force number one. What's force number two according to our ordering? Force number electromagnetic. Question. Electromagnetic is really how many words? Two. What's the first word? Second word? Magnetic. Question, everyone. How many people remember the basic rule of positive and negative charges? Opposites what? And likes? What's the word? Repel. So can I call it always attractive? Can I call it always repulsive? Could it be both? It is both depending on what situation you have. Okay, so it's the attractive or repulsive depending on what situation you're given. So the question now is, what does it act on? Like, what is this force relevant to? What kind of objects? The only thing or things that have to exist in the mix for this force to exist or to really play a role in either pulling things closer or pushing things further is what kind of electric charges are involved and what kind of magnetic what? Yeah, never call it magnetic charge, by the way. There's no such thing as a magnetic charge. There's a magnetic property, there's a magnetic strength, there's a magnetic behavior, but there is no magnetic charge. But there is definitely what kind of charge? Oh, yes, we know this, even from like grade school science. Okay. Do you think it cares about how big or how small the object is? What do you think? Did it mention anything about volume or mass? Nope, and it really doesn't. It doesn't care how light or how heavy the objects are. It doesn't care how they look. It doesn't care about the color. It just cares about what's the electron situation and what's the magnetism situation. Both things we will cover in 10 weeks, maybe. I don't know. Okay. So it only cares about how much electricity and or how much magnetism they have. What do you think the most important particle is to electromagnetic force? By the way, technically, a photon is important because light is what kind of a wave? Light is what kind of a wave? Electromagnetic wave. By the way, not just light. Gamma rays, radio waves, microwaves, all of the whole electromagnetic spectrum. But what other particle is important to this? Electron. So electromagnetic force is the basis of what kind of field of science? What does Miss Young teach? If electromagnetic force did not exist, by the way, what makes an electron jump between one atom and another? Yeah, energy. And what brings the energy level, or what makes the energy level do that? Electrical what? Attraction or what? Yeah, the electron is not happy in this environment. It needs to what? So it's repelled from the initial environment and attracted towards the what? The final environment, which is only through the what? The electromagnetic force. That's the only reason why they actually jump. Here's the thing. It is the strongest. You might ask, actually, what's holding you together? Why are you not right now disintegrated? You might say, oh, because gravity between particles. Is gravity still existing inside of us? I just said any things with masses have what between them? But do you think the gravity between the electrons and the neutrons and the protons inside of your body is enough or strong enough to keep you stuck together? Oh, if you only depend on that, you wouldn't exist anyway. So what do you think is keeping you tightly bound? What force? All the attraction between your what? Between your electrons and your, what's the positive ones? Negative ones are electrons. What are the positive ones? That's the only thing that's holding you apart. Gravitation is not strong enough. Yes. What do you want to say? Oh, someone had their hand up? Yes. If you remember, let me know. Okay? So the only thing holding you together is what kind of force? And that's why we know it's the what? But I'm having a legal disclaimer here. I'm saying it's the strongest where? Ah, okay. All right. It's the basis of chemistry. If that force did not exist, aside from physics itself not existing, but chemistry itself would not happen. Why would an electron jump around if it's not attracted or repelled? Literally, zero effect. Stay where you are. Be happy. Yes. No, go ahead. Listen up. Yeah. That's why. Yeah. There's nothing that's not okay. I could be actually safe saying there's nothing that's not related to electromagnetic field. They permeate the whole space and they affect everything. Okay? All right. Strong nuclear. Strong nuclear. Two names. By the way, you could get by or you could get away with saying just strong. Whenever a physicist talks about the strong force, they're talking about the strong nuclear force. There's no strong engineering force. There's only the strong nuclear force. Okay, I have a question for everyone. Usually, what does this represent? Come on. Is that saying? Yes, this is the International Atomic Agency symbol, right? Or whatever. What are those going around? Only what kind of particles? The only thing that could fly away so fast are what? Electrons. What's inside here? Look, what is the nucleus? It's a bunch of two things super freaking stuck together. Neutrons and, okay, everyone look. Makes sense, right? Let's shade some of them. The black ones are the neutrons. And the empty ones are the protons. Whatever. Question. What's the charge of a single neutron? Or actually, all the neutrons in the universe. What's the charge of them? They're neutral. So what's the charge? They have no charge. What's the charge of protons? How many people agree that protons are positive? If you bring two protons together and you put them right here, imagine you could hold them, and you let go. Would they stay where they are, get closer, move apart? What's the only rule that governs that behavior? Opposites attract, but likes. And two protons are considered what? Likes. So they should what? What the hell is happening here then? Yeah. That was the question they asked themselves 130 years ago. Why are they not flying apart? By the way, do you want them always to fly apart? Let's think about this. What happens when protons and neutrons fly apart? Anyone? How many people did grade 11 or 12 chemistry here? What happens when an atom loses a proton? Not loses or gains an electron. That's stupid. That's an ion. What happens when the building block itself kicks out or says hello? A proton or a neutron. Okay, if you gain neutrons, you become what? Isotopes, which is what? More radioactive, right? Heavier. What if you accept or lose a proton? It changes the atomic number, right? Which means it changed the what itself? The element itself. Carbon has how many? 6 protons, but 12 what? Whole things. No, 12 electrons in its neutral equal ion state. If you gain 1 proton, who knows what has 7? You just create a whole new element, right? Gain another one. What do you get? Is it making sense? And by the way, have you ever heard of the dream of making things into gold? Yeah, alchemy, 200, 300, 400 years ago. Technically, that could happen. Does anyone know the symbol for gold? Ag is silver, Au. I'm not sure what's the number for gold is. I think it's in the 20s. If you can bump enough protons and make what? Gold, you transfer the elements to gold. But you need what kind of a gun? A gun that fires what? Proton. Do you see what I mean? Theoretically and physically, it is possible. Do you think it's financially possible? Is it easy to get a proton gun? Of course not. That's basically a nuclear reactor, right? A particle accelerator. So that's my point. But here's my question, though. My question to you is what they asked each other, a bunch of geniuses of physics, 130 years ago. How come they're not going away? Sorry. There must be something what? Although the electromagnetic force says what? Says what? You have got to leave each other. Yet they're not. That was the only reason they come up with the what? They were like, okay, wait a minute. There's got to be another what? There's got to be another. Let's call it something. They called it what? First of all, they called it what? Because it only exists where? By the way, everyone, listen up. Listen, no, guys. The 3 people who won the Nobel Prize for actually discovering how this force works basically discovered this. There's a certain sweet spot distance. If the protons are not there, they will what? They will fly away like regular charges. There's a certain distance that if they what? Get what? So what? So close, what happens? The strong nuclear force overcomes what? The electromagnetic force. Is it making sense now? That's why it has a what? It has a certain range. If you hit it, you what? You coagulate. You stick together. If you pry, that's why whenever they want to pry them apart, do they need to pry them apart a lot? No, just what? Just a little bit to go beyond that what? Beyond that range. And then they will fly away. Question, everyone. What gives us heat and light? The sun. Does anyone know the reaction that happens in the sun? How can the sun produce so much heat and light and energy that actually we've been existing for so many years? Does anyone know what's the smallest atom in the universe? 1 proton. 1. Hydrogen. Hydrogen is just what? 1 proton and 1 what? Bring in another hydrogen. So far, are they close or far apart? So far, the way I sketch them. Very what? So do you think they're going to stick together or fly away? Yeah, a proton will repel this proton. How about if you bring them such that their electronic clouds overlap? Would they be then close enough for the what? Do you see what I mean here? It has a range. If you're within the range, it is what it is. If you're away from that range, guess what? A couple of charges just flying away. Yes. So how do they get in a range? Do you think it's easy to bring 2 likes together? The closer you bring them, what happens to your hands? You keep what? So it gets what? Well, what's so special about the sun? So, sorry, you need a lot of what to bring them together? Or do you think the sun has any shortage of energy? What does the sun do? Two hydrogens becomes what? Become what? What's He? The first noble gas. Helium. How many protons? Yeah, you stuck them together. Boom, that's it. Is it making sense? It uses a lot of energy to put them together, but then it produces a lot of energy when the reaction is done. And that's how we're alive. Yes? Uh-huh. Oh, and it could. You could actually, they actually found out up to, theoretically, they actually predicted that basically what? Usually only up to 3 or 4, I think. Because once it actually, here's the thing, once it actually bonds, it becomes helium, right? But then you're thinking about, oh, could I bond another helium with another hydrogen or two heliums together, right? That would be lithium. Lithium. But here's the thing. Once you bond them, they're still under so much energy. What's going to happen to them? Do you see what I mean? It's a continuous cycle of what? Production and destruction. Production and destruction. Do you see what I mean? But through that cycle, so much energy seeps in through vacuum and space and gets to us. But mainly, that's the main reaction that actually makes the sun what it is. H plus H equals He. What? Oh, it could disintegrate again because it's under so much energy. So you think the energy is bringing them together, but also what? And it's just making the whole cycle just keep going for billions and billions, like Carl Sagan said, for billions. It's recycled, but it also what? It seeps out and it seeps in. Yeah. When we talk about energy conservation, we'll talk about that mindset of energy is neither what? Created nor destroyed. Yes. Okay. Let's get with this. So, by the way, just so you know, listen up. The strong nuclear force is only what kind of force? It's only what? Attractive. It does not fly them apart. It brings them together. It's the binding force of neutrons and protons. Neutrons and protons. So it doesn't just act actually just on protons. It also binds them to neutrons too. It is the strongest inside of the nucleus. It actually doesn't exist literally outside of the range of a few protons. No effect outside of the nucleus. By the way, the ones who won the Nobel Prize for discovering this back in 2004 gave a very good analogy. It's like what? Look, everyone. How many people have seen a spring? Spring. What can you do to a spring? You can what? Compress it or? Okay. Stretch it. Stretch. What does the spring do the more you stretch it? Is it become easier or harder? Yeah. But at some point, if you stretch it just right enough, what could happen to the spring? Do you have a spring anymore? That's exactly what he said. He said it's like two protons are trying to get apart, and once they clear that range of closeness, it has no what? He said it's like a spring force. It gets harder, but if you just persevere and you have enough energy to pry them away from each other, guess what? You pry them away for life. How strong is the strong nuclear force? Well, does anyone know what that picture is on your Not quite. This is actually Trinity in New Mexico. This was the very first human-controlled chain reaction. This was the test site for the atomic bomb. That was a few months before they dropped it on what? Hiroshima on the 6th of August and Nagasaki on the 9th of August. Wiped out 2 cities. That's how strong it is. That was Trinity test site in New Mexico in the States a few months before those disastrous events. This is where physics became a nuclear weapon. Right then. This is the actual picture. It's digitally mastered because it wasn't this perfectly crisp back then in the 40s. This was the actual what? You know the mushroom cloud, right? About to form. Right there. How much time after? 0.025 seconds. Look how big it is after 2.5% of a second. 1/40th of a second, that much happened. This was witnessed by basically the creators of modern physics. Einstein, Fermi, Feynman, everyone was there. And that's when they realized they basically unleashed a beast. A few protons, you never think of them. Fry them away by a chain reaction, and you can wipe out 2 cities. And no, many more. Yes. Do you have an area anymore?
Well, no, but like,
Think about it. Every possible kind of energy is released. Thermal, radiation, sound, ground shaking, or like matter ripple waves, sound energy. You name it. It's completely wiped out. Energy, energy. If I just put you next to a big fire, what happens to you? If I put you next to a big fire, you're not touching it, but do you feel the heat? Bring the fire closer. What could it do at some point? It will actually what? Touch the particles, and then what? Give them enough energy to be completely what? Disintegrate or vaporize. It's an energy game. The more energy you put, the more damage you could do. Question. Everyone, did it shatter? What if I drop it from top of a building? But at least there's a maybe, and a big maybe, right? Why? When you drop it out of the building, what did you give it once you released it? Sorry, what is it gonna have right before it hits? A lot of what? Energy. Yeah, no. Acceleration is gonna be constant. It's gonna have a lot of speed, which means what? Impact. Thank you. It's always an energy game. All right. Last force. The what? The weak. What does this do? It causes one of the most important things, not just in physics, in nature. Nuclear transformation. When a proton, listen up, when a proton decides to switch into a neutron, when a neutron decides to switch into a proton, when an electron wants to disintegrate into a muon and a photon, when particles play the game of what? Shape shifting, it's because of which force? Raise your hand if you heard of quarks. Quarks. Q-U-A-R-K-S. Quarks. Say again? The thing that have corks. Cork, like bottle cork, like the little styrofoam that closes it. No. How many people have heard of quarks? Okay, everyone. This is just nerding out a little bit, but this is gonna be an interesting segue to really show you what this does. Eyes on the screen, pencils down. You don't have to copy this. Yes, please. Go ahead. Okay. Listen up. Does anyone here know how many types of quarks there are? If you know, that means you watch a few PBS documentaries. Layla. Yeah. But do you know how many? Because we have to pair them up. Everyone. And here are the names. Seriously, that's what they came up with. Up and. Okay, that's one pair. Called U and. By the way, they always use lowercase. The next one. Top and. You got it. Hey, you're becoming a physicist right there. Sometimes that's how easy the game is. Just come up with the names. So what do you think the symbols are? You can never guess the last two. They're weird. They're weird. Okay, I'll give you. They start with CNS. There's no way you're gonna get them. All right. Doctor Strange. And the only, listen up, and the only reason they call them that is because they discovered this one first, and this one opposite completely. Sorry, what do you call behaved completely opposite to it, so they called it what? Okay, we only. By the way, those are the ones we care about today. There's one particle made up of how many quarks? How many U's? Okay. By the way, those have charges. The charge of a U is what? Can someone tell me what do you get when you add? What do you get when you add plus 2/3? So 2/3 to 2/3, and you take away a third at the end. 1 whole, 3/3. A 1 whole that's positive or negative? That's how they discovered that a proton is made of what? 2 U's and a what? And a D. How about this one? How much is that? What has a 0? What has a +1? The people who discovered the existence of quarks won the Nobel Prize in 1990, 3 experimental physicists. You know how they did it? They collided them so hard, the protons, for a split second, shattered. And they were able to see what inside them? 3 what? 3 quarks? 3 quarks. One of them was a Canadian who won the Nobel Prize in 1990. My point is, question, what if you turn this into another quark? Do you still stay the same particle or something different? If you change this one into a D, what do you have now? That's what the weak force does. It goes so deep in, and it tells the quarks to what? To what? To shift. To basically what? Change who they are or what they are. And you got yourself what? You got yourself a whole new element because you either lost a proton or lost a neutron. Okay? It's responsible for breaking apart the inside of neutrons and protons, and by the way, other particles. But let's focus on these. And turning them into each other. Also, it only exists inside of the nucleus too. It has no effect if the particles are very, 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 very far apart. It causes nuclear decay. All parts of nuclear decay. How many people have heard of alpha decay, beta decay, gamma decay? All of these things, they would not have existed. By the way, is nuclear decay good or bad? When you hear of radioactive decay, well, okay. By the way, could it kill you? How many people have heard? Okay, what are the 2 most dangerous elements that give out a lot of radiation? The famous names for the stuff inside of the atomic bombs. One of them starts with a U, one of them starts with a P. Uranium and starts with a P. It's even worse. Not palladium. Plutonium. Uranium and plutonium. Okay, question. If you have a single, if I put a single milligram of uranium right here in my pocket, what's going to happen to me eventually? Cancer. Yes. Why? Because the radiation is going to go into my DNA and does what to the acid bases? They knock them away from each other. Boom! It changes my DNA into cancerous DNA, and my body, instead of producing what? Good cells, it produces what? Cancer cells. Okay. Could it also be life-saving? Yes. How many people have had an MRI before? CT scan. Boom! CT, X-ray. How many have had PET or SPECT, like nuclear medicine, when they inject you with a radioactive material and they trace it? Guess what? Anything that kills you could also have medical application. So nuclear decay, and by the way, nuclear decay is partially how this works. How this works? Because of sending signals. Nuclear decay is how Geiger counters and smoke detectors work, and radon detectors. So anything that's bad could also be what? Atomic bombs depended on good physics, but it was a killing machine. Okay? Yes. Yes, absolutely. Not chemotherapy, radiotherapy. Okay, so instead of knocking out good cells, now you're knocking out what? There we go. Yes, 2 ways 3. So engineering forces. So how many? As many as the problem requires. Sometimes, by the way, sometimes just one, sometimes two, three, four. It depends how complex the thing gets. Okay? There are many of these forces, since it really depends on what kind of physical situation is being studied. However, here are the only ones that we really care about in this course. What is this one called? Gravity, not gravitation. Different, related, but not the same. Number two. Okay, don't ask me why is it called, what's so normal about the normal force. Just relax. I'll tell you why it's called normal force. Number three. How many of you have heard of tension? Tension force. Number four. Could be your worst enemy, could be your best friend and lifesaver. Okay? Friction. Is friction good? Yeah. In 2 months, when you're driving in the snow and you want to really brake, that's going to save your life. Okay, we'll talk about that. Last one. Applied force. Applied force. Those are the 5 engineering forces that we really need to understand in this course. Gravity, normal, tension, friction, applied. Okay, so we have a slide for each one. Number one. Question, everyone. Can someone remind us how did we define gravitation? Gravitation is the attraction force between what? Between what? Did I tell you what the 2 objects had to be, or I said any 2 objects? Gravity, everyone listen up. This is the important principle here. Gravity is so specific. Gravity has to be between a what? A what? A huge object and a what? Tiny one, but the tiny one has to be on the what? It has to be either on the surface or very what? Very close. How close is close? Well, we'll talk about that. There you go. It's the force between a huge object. By the way, it doesn't have to be a planet. You still have gravity on the moon. Is it as strong as the Earth, though? No, but it still exists. You might say, so you might say, oh, so it just depends on how massive the object is. Yeah, but there's another factor as well. Very important. Just give me a second. I can't tell you exactly how very close is very close by. I'm just going to say this. As long as when you drop something on the surface, when you drop something, it really goes fast towards the surface, that's what we call what? Close by. Question. When you are on the International Space Station, are you close by to the Earth? Really? On the ISS where Commander Chris Hadfield was? No. How about on top of Mount Everest? Are you still technically close to the surface of the Earth? Yeah. How about on top of the Eiffel Tower? See, and yeah. So you see, it's kind of a relative thing, but at some point you have to say, I am not close, because you know what? If Chris Hadfield dropped something in the space station, would it go down? No, it would float as much as he does. Okay? Okay. We have to use different symbols now. But what is still the symbol for any force? Capital F with an arrow. But now we have to start using what? Little what? Subscript. What's the subscript for gravity? Can you guess? Absolutely. Yes. Everyone, I can't emphasize this enough. This G has to be what kind of a G? Lowercase g. So now you might think, oh, is there something with an uppercase G? There sure is. So that's force number 1. Force number 2. Normal. Question. Probably the answer is no. Has anyone taken calculus and vectors yet? Okay. Ladies and gentlemen, the word normal in calculus and in vectors just means perpendicular. Seriously. Normal in vectors means perpendicular. And that's why this force is called the what? The normal force. Everyone, if I, look, Did I hit the board? Was there a force from me to the board? Did the board hit me back? Oh, it did. It did. I felt it. Oh, yeah, I did. Did the board act back on me? What is the most famous Newton's law? Every action has a what? Here's my action. What's the proof that I have reaction? My hand hurts. Do you see what I mean? I hit it. It also what? But how did it hit me? Angled or straight out? I hit it in. It hits me what? How is the surface of this board relative to this marker? What's the angle between the board and the marker? 90 degrees. What does 90 mean? Perpendicular also means what? I just told you something from grade 12 calculus. Okay? So it is the force, a surface. By the way, anything that looks like a plane, even your hand. Push. No, push with a finger. It's like what? The fist and the what? And the board. Same thing. That's a plane. You're pushing. It's also what? Pushing back. You see what I mean? But he's pushing perpendicular in. My hand is also pushing what? Perpendicular out. Is it making sense? That's it. So, flat plane is all we need here. So, question. When can you only have normal forces? When you have what? You have to have a flat plane involved, and it's being what? It's being acted on as well. Any guesses for the symbol? G for gravity. Yeah, it's an N. Everyone, I like to use capital N. I've seen books with small n. I like to use capital N. Okay. Asser, what's force number 3? Tension force. Everyone, question. Is this under tension? What could happen if I tense it too much? Snaps, breaks, cracks, whatever. Tension? Is this tension? Is this tension? What do you call? What am I doing to my skin? What am I doing to my skin? Or what's another word for pushing in? Starts with C. What's the opposite of stretch? Compression. Compression, stretching. Okay, how about this? How about, what am I doing? Am I putting the lanyard under tension? How can you prove it? Once you let go, what's going to happen? So what did I do to this? Starts with a T. What kind of motion is this? Twisting. Anything that could withstand stretching, compressing, or twisting. By the way, does anyone know one word that could stand for all three? What do you call it when you, by the way, just a question here. When you, listen up, everyone, eyes on me. Is the mass changing or the shape? Does anyone know what do you call it when only the shape changes but the amount of particles stay the same, like mass? Starts with D. What happens when a baby is born with incomplete limbs? Deform. Deform is the actual technical term. Deform is the actual technical term when you change the shape. Can I deform this? Is this deformed? Could it snap? Could it snap? Could it? Yeah. I just have to keep what? It did. Right. I have a lot. Make sense? How many people work out here? Ooh, some people are just happy to say. Stretch marks. You see it? Lines, stretch marks. You know why? Because every guy here is going to do biceps curls every single day of the week for 7 days a week, right? What happens when you put the muscle under stretching and compression and tearing every single day? What happens to it? Does it ever go back? No. No. If you don't let it recover, does it ever go back? If you have a spring, actually no. If you have no. If everyone, if you have a rubber band, I don't have a rubber band, and you stretch it, sometimes you start seeing white in the middle, right? What is that white? Those are bonds broken, and they will never come back. That's exactly those. Is it making sense? You need recovery. You need to let it what go back a little. Is it making sense? That's what stretch marks are. Permanent deformation in the skin. Done. That's it. Okay? So deformed is the word that stands for all of these. Here's my question. Question, everyone. Where can you see tension? Okay. Officially in this course in grade 12 and even in first year, you can see it in what? Can you put a rope under tension? Is it under tension? Because it could snap. How about strings? Well, this could be a string too. How about cables? Oh yeah. By the way, cables are made of what? Cables usually are made of steel, right? Or metal. You could still stretch that. Springs. Question for you. Is this under tension right now? It is. There's a lot pushing on it. Do you see what I mean? Compression tension. Everything could be under tension. Even, okay, question for you. Could you do this to a brick? You can't. Because a brick, is a brick elastic? This could take the hit, right? Could a brick take as much? Maybe more, but a brick doesn't bend. A brick what? Snaps, cracks, breaks. Do you see what I mean? That's the difference. Do you know what we call something that could deform and kind of like go with the flow? Elastic. What do you call something that doesn't? Starts with B. B-R-I-T-T. Brittle. Brittle materials. Am I putting this under tension now? Do you think it could bend? A little bit. But at some point, it's not going to what? It's not going to bend. It's just going to what? It's going to snap. That's my point. Okay, so literally everything could be under what? Under tension. No exclusion. Okay. What do you think the symbol should be? Symbol. Come on. I've seen, and I would actually advocate either one of these two. I will mostly use the second one. Okay? But I just, you know why? Oftentimes you're going to have a problem with a lot of ropes in it. So I don't want to say FT1, FT2, FT3. Just say T1, T2, T3, and so on. By the way, I want you to circle this, everyone. Circle this and say most common. Circle this capital T by itself and say most common. Most common. Oh, the second symbol, sorry. This one, and write most common. So I would urge you to always use T, not FT. Okay. Munir, what's force number 4? Friction. Can someone explain to me what friction is? Don't use any big words. What does friction always do? By the way, friction does one of two things. It could either what? Yes, sir. Listen up, everyone. What could friction do to your motion? Slow it down. What could friction even do? Again? So we'll say that stopping is the eventual feat of slowing down. What could friction even do? It could even stop you from starting to what? From starting to what? To move. Think about it. Is there friction going on? Yeah. Why would you hear the squeaking? Is it moving? Do you think I'm still pushing? Is my push big enough? But it's still there, which means what? There's still friction. Do you see what I mean? Friction could either slow you down once you start moving, or what? or not even allow you to even begin what? Begin moving. Good. By the way, what kind of, okay, we have two kinds of friction, everyone. Listen up. We have this kind of friction. Look. I like to call this surface friction because it's an object on a surface. Was there friction when it was falling? Was it touching a surface? No. Okay. When something is surrounding something, we don't call that a surface. We call it an medium. Medium. Medium is anything you exist in. So there is medium friction. And what? Do you think we're ever going to deal with medium friction? No. We called it something before. Remember when we studied free fall? Air drag. We never care about drag. Drag is medium friction. Good. Okay. What is the symbol for friction? Any guesses? I mean, FF. You're right. Force of friction. Just make sure to make the subscript a smaller one. Sorry, like smaller in size and also in font. It's a lowercase. Okay. Last one. Ali, what's the last force? Listen up. What's force number 5? Ali? Applied force. What's applied force? Okay. The easiest way to understand what applied force is it's any force that you cannot say it's one of the first four. Is it making sense? Everyone, applied force is not gravity. You know it's not the gravity. It's not the force by the surface, because that would be what? What's any surface force? No, the surface when you push on it. Nor normal or perpendicular. Please don't say perpendicular. It is perpendicular, but the official name is normal. It's not tension, and it's not friction. Anything else is called what? Which means what? Something else isn't the problem. It's usually a person pushing something or pulling. So it's a force with which an external factor, like a person, tries to change the state of a system. Technically, as I just said to Haley, for example, it's any other force that you cannot say it's one of the first four. Okay? How many symbols? Honestly, listen up. It's anything you want, because you are basically calling it force of person. So you could say, for example, F subscript Mr. Ramadan. That would be the force of Mr. Ramadan pushing on the what? On the table. You could have a generic name. By the way, what does SOHCAHTOA stand for? Do you ever write sign S-I-N-E? What do you just write? S-I-N. You always abbreviate things to what? That's why APP is the what? Is the abbreviation for what? For force applied. Or you could just call it what? FA. What if you have 3 people and you don't want to use names? Person A, person B, person C, person D. FA, FB, FC, FD. Done. Make your life simple. I will give you full mark. Okay? So I don't really care what you call it. Okay? Just call it something. But just make sure that your F is capital, technically with an arrow on top. Okay? And those are the 5 forces that we have to contend with in this course. Okay? Gravity, friction, applied, normal, tension.